Okay, so before we actually get on to the sort of equations of cosmic dynamics, as I would call them, let's just look at a couple of key observables. But because these are things that you will see in the literature and they're things we will talk about later. And in particular, that's because the metric contains some important links back to the observable universe. And the most important thing it contains is it contains a scale factor. And so I'm going to write this slightly differently. I'm going to write 1 plus z is equal to lambda obs over lambda emit is equal to a t obs over a t emit. And what I mean here is that z here is the quantity we're going to call the redshift. Lambda is a wavelength. And these here are scale factors. And so the redshift, you could think of it as being the equivalent of a Doppler shift, but it is not a Doppler shift. Remember this, a Doppler shift is the result of objects moving through space-time. This is a result of the expansion of space-time in the expanding universe. But it makes the same effect on light. It stretches the photons so that they're observed at a longer wavelength than they're emitted, hence the phrase redshift. And that's equal to the scale factor at the time you observe them divided by the scale factor at the time you emit. So essentially, if the space-time is stretched, you could think of the photon as having its wavelength stretched by the scale factor. So if the scale factor increases by a factor of 2, the wavelength of the photon increases by a factor of 2. So you actually get a measure of the expansion of the universe between the time the photon was emitted and the time it is received by measuring the redshift. That's rather neat. And more commonly, you will say that the scale factor at the time you observe it, T obs, is equal to 1. In other words, the most useful unit to measure the size of the universe is in universes. So the universe is currently 1 universe big. And therefore, you can write that the scale factor at any given other time is equal to 1 over 1 plus z. So you measure the redshift and you get the scale factor. It's always smaller, of course, in the past because the universe has been expanding. You can also consider the differential of the scale factor. In a sense, that's the rate of change of the proper distance. So the proper distance, dp, is just equal to the integral r and d of the scale factor is just a of t d. And the radius here is just d, it's fixed, it's in co-moving coordinates. So in other words, you get the proper distance just from the change in scale factor. So what we want to do is now measure the change in dp. So v is equal to d by dt of dp is equal to a dot times d is equal to a dot over a dp. And you can think of this as V equals H naught D. So this is the Hubble constant at time t equals t0, i.e. today. Or more generally, it's the Hubble parameter, which can vary with time. And so this is just the scale factor, the rate of change of the scale factor, normalised by the scale factor at any given time. And so the redshift and the velocity are providing you crucial information about the scale factor and its rate of change.